Hello, this video is going to look at how to reduce first order differential equations. In our ordinary A-level we worked out how to solve differential equations of this sort, and we've got two methods, haven't we, two techniques. One is separation of the variables and the other one is the integration factor. Now the question is, how do we solve equations like the ones below? And it's the right hand side we're interested in. You can see there's combinations of x and y, but it's not possible to split them. And that's our problem. So what we need to do is to do some form of substitution for the right hand side, the x's and y's, so I end up with a single variable. So let me take you through that. Okay, here's our equation on the right hand side. I'm interested in this side here, and we have to look at it and see what might work. And you can probably see here, if I divided top and bottom by x squared, yeah, I would end up with a new version of the equation on the right hand side where I would have a y over x on the top, so it would become 1 plus 3 y over x squared, and on the bottom I'd have a y over x, because the bottom would become 2 y over x. And if I use the substitution here, and z equals y over x, I could rewrite the right hand side as 1 plus 3z squared over 2z. So I've sorted out my right hand side and it's entirely a function of z. And what I'm going to do is get an equation in terms of z and x. So I need to get rid of this dy by dx on the left hand side. So how do I do that? Well, if z equals y over x, then y equals zx. And I can differentiate that. Here we go. Dy by dx will equal dz by dx using the product rule, x plus z times 1. Okay, and I can substitute that into my differential equation here. So on the right hand side I put my z squareds in, and on the left hand side I replace that with the differential equivalent, and now I just need to get dz by dx on its own, don't I, in order to do this. Get ready, particularly if I'm going to do it by separation of variables. So what am I going to do? I need to get rid of that z, so I'm going to subtract z from both sides. There it is there, coming out, and then I simplify. There we are. So now I've got x dz by dx equals 1 plus z squared over 2z. Well, you can probably see that we can integrate that. We can solve this by separating the variables and integrating. So next line, I've put the z's on the left hand side, x's on the right hand side. I integrate that. I'm going to have a ln on the left hand side, I'm going to have a ln on the right hand side, and don't forget your c. And therefore if I power up this equation, so those become the powers, these two values, then I get 1 plus z equals some constant times x. Remember, I've just changed a is going to be equal e to the c. We don't want to be bothered writing e to the c the whole time for our constant of integration, so I've just called that a. So rearranging, z squared equals a minus x, and rooting z equals, I should probably have plus or minus ax minus 1, but I'm probably going to work on the basis that if I was turning it into a function, I'd have x and z, or certainly the z would be greater than 0. There we go. Then I need to transform it back. Well, that's easy enough to get to my y's. So y equals zx. So therefore, substituting this in place of z, I get y equals x times the square root of ax minus 1 as being my general solution. So have a look at my second example. Well, again, I've got a mixes of x and y's and I can't separate it. But what I can see is I've got the same pattern here, combination of x's and y's. So I'm going to use that as my substitution. So z is going to equal y minus x. So I can rewrite my right hand side would be z plus 2, z over z plus 3. I've achieved my objective. I've got a single variable on the right hand side. So using that substitution, z equals y minus x, I can rearrange that to get y equals z plus x, and that means that I can get an equivalent for my dy by dx, because it must equal dz by dx plus 1. Now I've got all the bits that I need to substitute into my differential equation here and convert it from an equation in y and x into an equation in z and x. So there we are. That's the differential. Here's my z in place of my y minus x. Get my dz by dx on its own by subtracting 1 from both sides, which tidies up to this equation here, differential equation. Dz by dx equals minus 1 over z plus 3. Good. So I'm going to use separation of variables again to solve this. There we go. Excuse me, let's go back up one there. So I'm just going to split the variables, so I've got z's on this side, x's on that side, and integrate it. So I get this almost quadratic in z coming along here. No, z squared plus 3z on the left hand side. I've got some minus x, and I've got my constant of integration. Remember that always during that step. I now need to get back to y because I'm trying to solve for y. So I use my translation, my substitution, my original substitution, z equals y minus x, sub that into this equation here. So I've got it there and there, haven't I? My substitutions, do a bit of tidying up, and I end up with this general solution. There we go. So there you have it. If you get problems like these ones here, where the variables are mixed on the right hand side, we need to find a substitution by what they call inspection, by looking at it, that will tidy the right hand side up into a single variable z. In this case it's y over x, in this case it's y minus x. We then create a differential equation which is going to be in the form dz by dx equals something, which is a combination, a split combination of x's and z's, and at the end we transform back to y to get our solution. So there you have it. Hope that's of use.